In general, this part of our meetings, our lectures are devoted to the study of neutrino electromagnetic properties. Neutrino electromagnetic properties. So this is really a key issue of the research that have been conducted and are conducted in our research neutrino group for many decades, I should say, for 3 decades. Yeah, and just for information, I would like to announce the widest review on the subject that have been published in 2015 by my colleague and friend Carlo Giunti, from Torino, and myself. And the title is of neutrinos, a window to new physics. This was published in Reviews of Modern Physics. If I properly remember, the volume is like this, the year is like this, and the page is like 31 to 60 pages. This is about 591. Available on archive. This is the most wide review on the subject, and most of the topics that we shall discuss today or just during the lectures can be found, but it will be a little bit simplified. Yeah, I'll say. Well, so just to start continuing calculations that we have performed last time, I would like for newcomers just to recall the present fundamental knowledge about the properties of neutrinos. So first, we know that the mass of neutrino, I equal to 1 to 3, is not 0. This is a fundamental fact that comes from experiments. Then there is mixing and oscillations between neutrinos. So there are flavor neutrinos, F equal to electron, muon, and tau neutrinos. Then they are marked or determined or labeled by the Lagrangian of interaction of electroweak theory. So in the standard model, Lagrangian of the standard model has such type of interactions, the electron neutrino to electron, and this is charge boson. This is how we label, how we distinguish these neutrinos. The similar diagram in the standard model exists for muon neutrinos and for tau neutrinos, and correspondingly here will be muon or tau leptons. Yeah. So this is definition and the role of flavor neutrinos. According to the idea that was first formulated by Bruno Pontecorvo, in 1957, there is a mixing between different types of neutrinos. Also, at the time, there was no notion about different types of neutrinos. The muon neutrino was discovered in 1962, and Pontecorvo spoke about mixing and oscillations between existed or known at that time 2 types of neutrinos, that were recognized as neutrinos and antineutrinos without identification of the flavor. It was like a neutrino that originates from, appears or produced in the beta decay of a neutron. As electron antineutrino, there was just a neutrino. And Pontokorova just make a statement that if the mass of neutrino is not zero, then neutrinos should be considered as the mixture or superposition of different types of neutrinos and antineutrinos. And that was his first claim, first statement. And the second statement was, there were two papers published in 1957. The second statement by words, without any formulas, that as a result, on a certain distance from a reactor, and the reactor was considered like a source of neutrinos, the flux of neutrinos will be composed of equal amount of neutrinos and antineutrinos. And this is the result of oscillations, as we know. Then, in '62, Japanese group Maki, Nakagawa, Sakata, after the discovery of the second type of neutrino, or it was discovered a neutrino that was not equal to electroneutrino, it was termed as the muon neutrino. So in '62, two neutrinos appears, yeah? And the third neutrino was discovered in 2000, in 2000, yeah? Just very recently, just about only 24 years ago. Well, and after this, then the understanding came on the market that there are at least two types of neutrinos. Immediately, Japanese people, Maki, Nakagawa, Sakata, they generalized this idea of Pontokorova, and they just implemented or just claim that there is mixing between not neutrino and antineutrino, but between electron at Maki, Nakagawa, Sakata in the same year, and they just consider mixing, not oscillations, between two different types of neutrinos. And this is particular people who just introduced the mixing angle. They just introduced the mixing matrix U, as we use if we consider the two types of mass states and two flavor neutrinos. That was their notion. And they just say that it can be parameterized by the mixing angle. So this is quite important opening or idea of these people. But they have, they failed to go further. And they didn't follow the second statement of Pontokorova of 1957, that after a distance a bunch of neutrinos has traveled, there will be an equal amount of two different types of neutrinos. That is a result of mixing. So they just introduce this, but in like a stationary point. They thought that this is just a parameterization, and they failed to understand the real fundamental meaning of this phenomena. They just put it just convenience, and they even did not raise the question, and what will be happening if the flux of mixing neutrinos will propagate in space and time. And only in 1969, Bruno Pontokorova and Gribov just consider the dynamics or kinematics of these mixing neutrinos, and they derived the first time the stellation probability that describes how neutrino of one type converted to neutrinos of another type in space and time. So they just derived the formulas that we use now. But there was a mistake. They just missed 1/2, but it's not important. So this is more or less the history of neutrinos. And now I would like to turn back to the main subject of our lectures, and I would like to flash to electromagnetic properties. Initially, when Wolfgang Pauli in 1930 proposed the existence of neutrino, and he called it neutron, as you know, yeah. And only after the discovery of real neutron, neutron was discovered in 1932 by Thomson, yeah. And Fermi Enrico Fermi renamed neutron of Pauli to neutrino, small neutral particle. Yeah. Well, when Pauli introduced, let's call it neutrino, he proposed that this is particle of or is a fermion. The mass is 0, most probable, and the charge of neutrino is 0. And probably magnetic moment is not 0. Probably is not 0. That was the prediction of what Pauli just thought about this particle he introduced in 1930. Now, what is the present status of these properties of neutrinos? For sure, we know that mass is not 0. The mass of neutrino is not 0. This comes from two sets of experiments of observing the fluxes of solar and atmospheric neutrinos. Neutrino from the sun. This is solar neutrinos from the sun and neutrinos from atmosphere. So experiments detect the fluxes of neutrino from the sun, from atmosphere here on the Earth, and the results cannot be described, the fluxes, experimental fluxes, cannot be described by the standard model. So the standard model failed to describe, to explain the amount of neutrinos that arrive on the Earth from the sun and the amount of neutrinos that are detected in the detectors and the neutrinos that are generated by interaction of cosmic rays with the atmosphere about 10 or 15 kilometers above the Earth. So, and no any way can be found out except adaptation or just confirmation that there is a mixing and oscillations between different types of neutrinos, and according to the formulas that we shall also use today, I hope, it just follows just an obligatory fact that the mass of neutrinos should be not 0. And we know that there are 3 mass states of neutrinos, and here it's better to speak about the masses of the mass states of neutrinos. And again, from the pressure of the results of these 2 experimental facts, we can conclude that there are 3 masses of neutrinos, of mass states neutrinos, and at least 2 are not 0 and not equal to each other. So among these 3, 2 not 0, and they are not equal to each other. So I don't know how to write this. 2 are not 0. Mi 0 mg, yeah, and mi not equal to mg. This we choose a pair of I and J, and then we should say that they are not zero and not equal to each other. This is because the oscillation probabilities that are used to describe to provide the solution for the solar neutrinos depends on the mass square difference of 1, 2, that equals to the mass 2 minus mass 1 squared, yeah? And this should be not zero. For the atmospheric neutrinos, another scale of mass weight difference should be needed, and the atmospheric flux is sensitive to this combination of squares of the masses. Well, and this should be not zero again. Well, and they must be different. They must be different because the fluxes are different here. And the results of suppression of the electronic neutrino flux in the case of solar neutrinos and muonic in the case of atmospheric neutrinos have different degree of suppression. So this delta m1, 3 and delta m squared and delta m1, 2 are quite different values. So this is the best what we know about neutrinos. But in addition, there are direct searches, experimental studies and attempts to measure the absolute value of these masses. And from experiments, I just called the latest, the best experiment, Catherine collaboration. This is a Karlsruhe in Germany. From 2019, they just have the best upper bound on the mass of neutrino. This is the effective mass of neutrino less than 0.08 electron volt, so a little bit less than one electron volt. Okay, this is the present knowledge, the present status of the masses of neutrinos. Now let's turn again. Once again, this is numerous attempts just to start speaking about neutrino electromagnetic properties. Yeah. Now let's go back to the main line of our lectures. Electromagnetic properties. Well, and let's recall the Stern model. And because interactions of masses of flavor neutrinos are described by the Lagrangian of the Stern model. Yeah? Well, obviously, from all these definitions and the properties that I just flashed, of neutrino properties I just has flashed, follows that the flavor neutrinos has no mass. Because if each flavor neutrino is a superposition of different neutrino of different masses, you can't introduce in a normal way, in a regular way, the mass for the flavor neutrino. Because the mass is a value that enters the equation of motion, Dirac equation. Yeah? And if you write a Dirac equation for the mass states of neutrinos, and let's say that flavor neutrino is a superposition of bodies with different masses, you cannot write an equation for the flavor neutrino like a Dirac equation. Yeah? Okay. But interaction of neutrinos still describes by the Lagrangian of Stern model. And there we have flavor neutrinos. And in this Lagrangian, we have a flavor neutrino, electron neutrino, that can interact with, if it is flavor fixed by electron, with an electron. Again, electron neutrino. And here there will be the W boson. Yeah, this is what the standard model for the flavor neutrino predicts. Yeah. No, similar diagram exists for muon neutrino and tau. Here you just put muon and tau. Yeah, okay. And if you remember, these kind of diagrams, due to this radiation loop, can produce interaction with photons. And this interaction, if the charge of these fermions, like neutrinos, is zero, if we just suppose that the electric charge of flavor neutrino is zero, as it is in the standard model, then this diagram gives a contribution to the anomalous magnetic moment of neutrino. And for the case I just indicated here, the case when the electric charge is zero, this is the anomalous magnetic moment of neutrino, but people normally do not mention this is anomalous, just saying that this is the magnetic moment of neutrino. So, and this diagram can be interpreted or written using the mass states of neutrinos. So, what we can say? Here we put what we know about flavor neutrinos, that they are a superposition of the mass states. And I just generalize this diagram to a more the general to the today's vision what is neutrinos. So I just write such an effective diagram. Here I put the mixing matrix, this mixing matrix. Mixing matrix, and I decomposed this flavor neutrino to the mass states of neutrinos. And here I put the mixing matrix. Yeah. So each flavor neutrino is a sum of the mass states of neutrinos. F equals to electron, muon, and tau. And I equals to 1, 2, and 3. So each, this is what we know about neutrinos, that each flavor neutrino is superposition of the mass states of neutrinos. And I just make this decomposition. And as soon as this is neutrino 1, neutrino 2, neutrino 3, and as soon as this is the mass states, we can just put here, I don't want to write an exact expressions, but this is the diagrams that contribute here. Each of and then I again make like this. Oh no, I probably have a mistake. Yeah, here I should write neutrino 1, and here I should write neutrino 1, and here I should write electron, muon, and tau neutrinos, and that will be electron, W, tau, muon, tau, and W. Okay. So we know how, this is the standard model contribution. And then I go back, I just again put here the mixing matrix, and I reconstruct back to the neutrino of the mass M1. And from this we can conclude that just incorporating the notion how flavor neutrino interacts with the charged particles, so we can calculate this diagram, and that we know in the case of similar diagram for the electron. Yeah. So if you just put the similar diagram for an electron. We know that this diagram will give contribution to the anomalous magnetic moment of electron. Yeah? Here we just put an effective electron neutrino. Yeah? So we can put here the interaction with the photon, and the standard quantum electrodynamics and electroweak theory produce the anomalous magnetic moment of electron. Yeah? Anomalous magnetic moment of electron. Of an electron. The normal comes from a Dirac equation, you know, yeah? This is an addition due to radiation polarization loop, yeah? In case of neutrino, if we suppose the electric charge of neutrino is 0, if we suppose, but there are some theoretical framework where neutrino can be charged, electrically charged particle, and we call it Millicharged neutrino, but it's another story. Well, and just these calculations result in the following, that in the case of the Dirac neutrino, for the case of the Dirac neutrino, the contribution to the magnetic moment of Dirac neutrino proportional to the mass of the particle. This is coupling, Fermi coupling. This is the mass of neutrino divided by 8 square root of 2 pi. This is approximately, if you just put the numbers, this comes from the propagator of W boson. You know, this is non-local interaction, but if the mass, if we consider the case that the energy are not very high in respect to the masses of W boson, this coupling, the propagator of W, gives you the Fermi coupling that is inverse proportional to the mass of W boson. Yeah, it just comes from the exact expression for the propagator of W boson. Yeah. So, and if you put the numbers, that will be 3.2, 10 minus 19. If we measure the mass of neutrino, we scale it in EV, 1 EV, multiplied by the Bohr magnetron. Bohr magnetron is mass of electron. This is Bohr magnetron. This is a fundamental fact in the neutrino electromagnetic properties. So if we accept, but it is proven experimentally, that the mass is not 0, then magnetic moment of the mass states of neutrinos will be not 0. At least 2 of 3. Yeah? So we have 3 different magnetic moments. And from what I have just told you, that from experimental studies of the fluxes of the solar and atmospheric neutrinos, it follows that at least 2 masses are not 0. At least. It's not possible that 2 masses are 0. Because in this case, 2 mass square difference will be equal to each other. And there is no chance to simultaneously explain the flux of solar and the deficit of electron component in the solar neutrino flux and the deficit of the muon neutrino flux in atmospheric neutrinos. So it should be 2 different mass square differences, and it means that and they should be not 0, And it follows that at least two masses are not zero and not equal to each other. So it means that at least two of these guys are not equal to zero. And they're different, because all masses of three neutrinos are different, even though one can be zero. Yeah? So this is what is a solid experimental consequence if we believe that interaction of neutrinos are governed by the standard model, interaction Lagrangian, and if we adopt the fact that there is mixing between mass states and neutrinos, and each flavor of neutrinos as superposition of three different mass states. And also, we just incorporate the results of experiments that just put all our theoretical exercises to a more concrete way, and we get this very important result. It means that electromagnetic properties of neutrinos are not trivial. So it is not possible to say that neutrino has or have, if we consider many neutrinos, zero magnetic moment. So this is, and also this is a tiny value, by the way. Yeah? It is a tiny value. If you remember the electron, this is an anomalous magnetic moment of neutrino. Yeah? If we just put the Catherine limit, Catherine set a limit of about 1 eV or 0.8 eV, yeah, on the effective mass of neutrinos. This is a combination of masses multiplied by the elements of the mixed matrix. So it means, but elements are more or less around about 1 or less than 1, but not tiny. Yeah, okay. So it means that Catherine limit more or less give a notion or feeling what can be the mass of the mass state of neutrino. Well, it is maybe 1/10 or 10 to minus 2 or something like this. Well, however, there are different theoretical models presently on the market that provide quite different prediction for neutrino magnetic moments, not like this from the standard model interaction. And for instance, what you are studying the supersymmetry, yeah? Well, in the supersymmetric theoretical framework, it is possible to find an option when the magnetic moment for neutrino will be many, many orders of magnitude bigger, larger than this. Also, in some models of great unified theories, etc., when there are new interactions, it is also possible to get not 10 to minus 19, but 10 to minus 12, 13, 14, so many, many orders of magnitude larger than the prediction of the, as we call it, the easiest generalization of the standard model. Easiest generalization of the standard model. Okay, what is the present experimental status of magnetic moments? So there are several, many experimental investigations, and terrestrial experiments. For instance, JEMMA. This is JEMMA collaboration. This is in Dubna. It's Joint Institute of Nuclear GINR, yeah? GINR, Joint Institute of Nuclear Research, plus Kurchatov Institute, ITEP. Now it's ITEP. It's Kalinin nuclear power plant. They use the flux of reactor neutrinos. Antineutrinos, And the limit that they get is like 2.9 10 to minus 11 Bohr magnetrons. So they consider the scattering of neutrinos on electron of the target, and the cross section is composed of two terms. This is the standard model contribution, just weak contribution standard model that is proportional to the Fermi coupling constant squared, yeah? Plus electromagnetic contribution. The standard model is electromagnetic due to magnetic moment. It is proportional to magnetic moment of neutrino squared. Yeah? And they measure this since many years. So I think that the first result, the first result was announced in 2000. The latest result was announced this one. The first was something 3 10 to minus 11. So, well, surprisingly, they see nothing. So all this is for sure not zero. Of course, nobody canceled the standard model contribution. Yeah, both terms exist, but they are beneath the background. You understand? Yeah. So it means that each of these terms is smaller than the background. Well, and if this value is smaller, a particular number, you immediately get this limit that the magnetic moment is less than about 3 10 to minus 11. This is the best reactor neutrino bound. So a similar ideology has been used with in the investigation of the solar neutrino fluxes. And the best up to now, Boroxino experiment. No, normally people just write it like this, Boroxino. I don't know why. Boroxino collaboration. This is Gran Sasso in Italy. Gran Sasso National Lab. Gran Sasso. This is a mountain, Gran Sasso, about 3 kilometers height, and about 150 kilometers from Rome. And inside this mountain, there is automobile tunnels that was constructed to make easy for from Rome people to go to the sea. And it was constructed in 70s. And a very smart, still alive Italian physicist, Zecchicchi. He is famous for his studies also in gravitation, in gravity. And he just proposed, well, you just spent a lot of money to make these two tunnels. And the length of the tunnel about 11 kilometers. There are two lines. This is Gran Sasso, and there is two lines of tunnels in two directions. In one direction and back. So this is the sea, this is Rome. Yeah? And he just said, and here is CERN. CERN. And he just said, well, it was 70s, yeah? Well, if you just spent a lot of money, it's 3 kilometers high, yeah? 3 kilometers. Let's make 3 caves in the direction of CERN, in the middle. And they make these 3 caves, A, B, C, about 50 meters long, about 20 meters high, and about 50 meters wide, well, like grand halls, exactly direct to CERN. Just that was idea, and one of the best experiments and the famous experiments that confirmed the existence of neutrino oscillation phenomena was located in one of these halls, I don't remember ABC, I don't know in which one. And they just catch neutrinos, small neutrinos coming from CERN along this hole, and there is a huge installation, opera experiment, that detected tau neutrinos in initial flux of muon neutrinos that started 735 kilometers from CERN, directed to this hole that was constructed by Zekike. And the experiment started about 20 years after this hole was constructed. So what it means how powerful this guy, Zekike, was, that he convinced the government and business people to just excavate an additional holes for scientific reason, yeah? So, and here in one of the holes, the Boruxine experiment, it is a big tank with insulator that catch neutrinos that come above the Earth through this mountain to this tank, and they measure the flux of solar neutrinos, electron neutrinos, and they also has a limit on the magnetic moment Boruxina of neutrino that is slightly less, 10 to minus 11 Bohr magnetons. This is in fact, this is a little bit different combination of fundamental neutrino magnetic moments that is introduced in the basis for the of mass states of neutrinos. But nevertheless, there is some communication between those values. And the best limit from the solar fluxes has been obtained recently by Xenon. And T experiment, also with solar neutrinos, and this limit, Xenon, is something 6.2 10 to minus 12 Bohr magnetons. More or less better. Also astrophysics, astrophysical consideration provide a limit on possible neutrino magnetic moments from astrophysics, and I would say that the first astrophysical limits on neutrino magnetic moments just come from studies of Raffelt, Greg Raffelt. This is famous German scientist, neutrino physicist, and astrophysicist in 90, I think, something like this. And this limit is like this, 3, 10 to minus 12 Bohr magnetons. Slightly better than terrestrial limits. And it comes from the consideration of cooling of stars. So if magnetic moment of neutrino is not 0, then an addition contribution to production of photons that provide the cooling process of cooling of the star appears if magnetic moment is not 0 of neutrinos. Then this coupling appears, and this disturbs the observational picture of cooling, of evolution of red giant stars. And again, there are some flexibility. They observe the phases of emission of energy, and this is an extra energy deposit process that make faster this process. And compare this contribution to the observational data, they get that this process can give more than what we can see, that is acceptable from the observation. And this is astrophysical constraint that was many years ago. This idea was there are a little bit more strong constraints, but this the present number, the people study in more detail this process. Some new experimental observational data appears to this year, and this number now is something like 1, 5, or a little bit smaller. But the idea was was put forward by Raffelt for the first time. And now I would like to mention that the charge of neutrino can be also not zero. There are some generalizations of the standard model where it is possible to introduce, without any contradiction with the theoretical framework, that neutrino is a charged particle. But, and we call it the Millicharged neutrino, Millicharged neutrinos, yeah? And the most severe bound on the Millicharged of neutrino comes from the neutrality of the hydrogen atom, or equality of the charge over proton and electron, I mean modulus, yeah? So if you just consider this process, this is plus, this is minus, these charges are measured with some accuracy, and if you don't want to destroy everything in the world, saying that the charge is not conserved, you should believe that the charge is conserved. So it means that neutron is a neutral particle from experimental point of view within the uncertainty of the measurements of the charge of the proton and electron. Yeah? Or also the hydrogen atom is a neutral body, but again, this is to some experimental uncertainty. Yeah? Everything is confronted by experiment, but experiment is not absolute. All data from experiment has some uncertainty. Yeah? Well, and if we just compare this charge or the fact of neutrality, experimental fact of neutrality of hydrogen atom, the most severe bound on neutrino electric charge or Millicharged is like this, charge of electron. This is the best, the most severe bound, experimental bound. However, again, there are different experiments that also examine the possibility that neutrino has non-zero Millicharge. And in particular, the JAMA experiment I just mentioned also, just about 10 years ago, from JAMA. This was in 2014. I just added to this analysis of the cross-section of neutrino on electrons in JAMA data. There are, as I just mentioned already, the standard model contribution that is governed by the Fermi coupling. Then there is contribution from possible interaction of neutrinos with a non-zero magnetic moment. And then, if you suppose that neutrino is a Millicharged particle, I just add here the third term that comes from interaction of electron to neutrino Millicharge. That is proportional to Millicharge of neutrino squared. And again, nothing is seen, so it means that this guy should be less than the background, and I just obtained that the Millicharge is less than probably 1/3, 10 to minus 13 charge of electron. And since this year it is considered as the best reactor experimental bound on neutrino Millicharge, and it is published in the set of properties of neutrinos by the particle data group. Particle data group collaboration. This is a group of about 100 most distinguished people that issue each 2 years a volume of nearly 2,000 pages with a set of all properties of all interactions of all particles, including neutrinos. And a special part is devoted to neutrinos, and this result is mentioning as the best limit from terrestrial experiments. There are another limits also from astrophysics, etc. By the way, and the best astrophysical bound also come from our paper with my student and postgraduate student, Ilya Tokarev, and the astrophysical bound on neutrino Millicharged. That is something like 1.1 10 to minus 19 charge of electron. This is from my paper and Ilya Tokarev, Nuclear Physics B, 2014. So what we have done, there is a pulsar. If there is a magnetic field and if the charge of neutrino is not zero, magnetic field, and there is a rotation of pulsar with some velocity. So during the evolution, most of the energy in the process of neutron stars and just gone away with the flux of neutrinos. And if there is no magnetic field, neutrinos will escape perpendicular to the surface. If the magnetic field is not zero, neutrinos will be moving on the curved orbits, and they will be like this. So, and there is a torque momentum, yeah, that is produced by Millicharged neutrinos moving in a magnetic field and escaping the surface. And this can disturb the rotation of the pulsar, and we just introduce, we call it neutrino star turning mechanism, like a new ST mechanism. And due to impact of this neutrino star turning mechanism, there is a shift of the velocity of the angular velocity of the pulsar, and we just make a criteria that this shift should be less than observable rotational frequency of pulsars, like we say, like this. And this depends on the charge of neutrino. This depends on the charge of neutrino, yeah? We calculate it in this paper, and we get this limit. And this is the most severe astrophysical bound. And also it is accepted by other people. So just this is like, probably in one of the lectures I will just, we shall discuss how this torque was calculated and how this limit was obtained. Okay, so I think that I even has done more than I planned really in this introductory part, and now I would like to turn to real calculation and real theoretical consideration of neutrino electromagnetic properties and what are new phenomena that are related and are engendered by non-trivial neutrino electromagnetic properties. Of course, the most acceptable and the most widely discussed are magnetic moments of neutrinos. But of course there are some other, in addition to this magnetic moment, Millicharged. If you even suppose that neutrino is a Millicharged zero charged particle, neutrino can be considered as a superposition of effective superposition of clouds with opposite charges, and in this case the people introduce, and it is one of the properties of neutrinos, like a charge radius. So the object is has zero charge, but it has a charge radius. So the classical the classical model is there are two clouds with opposite charges, equal amounts of these charges. They overlap. The charge is zero, but it has non-trivial electromagnetic properties. And I would say that this charge radius is the most easily accepted to be observed in experiment, because this charge radius also contribute to the cross section of neutrinos on electrons, let's say. And even in the standard model, there is no need to go beyond the standard model. Even in the standard model, the charge radius is not zero within the standard model calculations. And only one order of magnitude accuracy should be needed. Improvement of the measurements of the cross section is needed to feel or to observe the charge radius of neutrino. So it is not so popular just among people, but it is the most easiest, the most close to our ability to observe in the experiment. Because of course, just to move from 10 to minus 19 to 10 to minus 12 or 13 in the magnetic moment investigation, it is a very hard job, yeah? Also, the hope is that there are some theory that beyond the standard model and that predict much bigger magnetic moment that is predicted by the standard model itself, yeah? Also with the Millicharged, also you should create some very complicated theoretical addition to the standard model to have this non-zero Millicharged of neutrino. But what is concerned the charge radius, nothing should be done with the theory. This charge radius exists inside the standard model. So this is the standard model prediction. The Millicharged, in one of our lectures, we shall consider the electromagnetic vertex function of neutrino in most general case and decomposition on the form factors. And one of the form factors gives just a Millicharged of neutrino. Yeah? And it is very close to reality, I should say. And I think that maybe in 10 years, if just the progress in measurement, the cross sections of neutrinos will be like in the previous decade, people will see the contribution of the Millicharged, of charge radius to the cross section. So, but I don't want to speak about this because probably we shall have a special lecture when I discuss with you the decomposition of the electromagnetic vertex function on the form factors. For form factors, in addition, there is an anapole form factor, probably you have heard from the general courses of quantum field theory. Well, also it's related somehow to a Millicharged, to the charge radius, yeah? And experimentally, it is very difficult to distinguish them. Okay, and now let's concentrate on the magnetic moment of neutrino. Of neutrino. Obviously, this value is not zero. I just convinced you, yeah? If you believe that neutrino is a massive particle. Then in Lagrangian, we have an additional term that being together, neutrinos, different neutrinos, so it's equal to 1/2 neutrino bar this magnetic moment, this like a coupling, this neutrino bar sigma ij with electromagnetic field. Plus, so if magnetic moment is 0, we get this additional term in the Lagrangian. It describes interaction of neutrinos with external electromagnetic field. Neutrinos we can decompose in two chiral or helicity states. Yeah. So neutrino can be expressed like a left plus neutrino right. Yeah. Where neutrino left equals to 1/2 1 plus gamma 5 neutrino, and neutrino right equals to 1/2 1 minus gamma 5 neutrino. Yeah. Well, it is quite easy to show that this term is decomposed. This is gamma 0. Yeah. You know, yeah, this bar is gamma 0 here, additional. Yeah, it is quite easy to see that this reproduce the following interactions. This is like right sigma ij f ij sigma left plus mu sigma left right. So if we consider left and right neutrinos as a different neutrino species, different chiral states, then we see that even in the interaction Lagrangian there is a mixing between different neutrino species. So, and as a result, just taking in mind the analogy in the case of mixing of the flavor neutrinos, of the mass states of neutrinos, we can see that there exist if we just consider this Fej like the magnetic field, then we see there is a mixing between left and right neutrinos. And as a consequence, we can introduce a new phenomena, mixing and oscillation of spin states of neutrinos. And we arrive to a new phenomena, spin oscillations of neutrinos in a transversal magnetic field. So we decomposed the magnetic field to the longitudinal part plus transversal part. And just in our further calculation, we show that the transition between left and right neutrinos are completely determined by interaction with transversal magnetic field in respect to neutrino propagation. And the longitudinal part only shifts the energy of each of neutrino species, but does not produce a mixing. Also, this part is suppressed by inverse Lorentz factor. If you just recall the Lorentz transformation of the electromagnetic field tensor or magnetic field from the laboratory frame to the relativistically moving in a spectral laboratory frame related to neutrinos, you will see that this part will be just diminished because this will be reinforced by the Lorentz factor in the transition from one laboratory frame to another, and this will have not this increase. So it means that normally people, when they are speaking about influence of magnetic field on neutrinos, in particular, discuss the mixing and oscillation of spin oscillations, they mostly, especially in the beginning, they mostly speak about the transversal magnetic moment. They keep out this longitudinal part. Okay. Well, also, this Lagrangian can be generalized when we consider different types of. I didn't mention which kind of neutrinos are here. I just suppose that this is left and right, the same type of neutrino. But it can be that this is neutrino like a neutrino of the type I, sigma of type alpha, let's say, ij, f ij, and here is the neutrino of type beta. Alpha is not equal to beta. Then the coefficients here should be alpha beta, and this call is of diagonal magnetic moment or transition magnetic. Sometimes magnetic is mixed, transition moment. So this is again a transition between left and right neutrinos, but with different masses. This is a la magnetic moment interaction with external electromagnetic field, but in addition, the type of neutrino is changing. So left-handed neutrino of mass 1 is converted to the right-handed of neutrino of mass 2. So in addition, mass is changing. And these magnetic moments, these coefficients, are called transition magnetic moments. Transition moments of diagonal. They are not diagonal. Yeah? And here I would like to mention, to recall that, in fact, another very important open issues, questions, fundamental questions not solved yet in neutrino physics, is what is the type of neutrino? If we should suppose that the mass is that the charge is zero, then we come to the crossroad. Whether neutrino can be the Dirac particle or Majorana particle, you know, yeah? Well, because for electron it is not, it's meaningless, because electron is for sure not equal to anti-electron to the positron, because the charges are different. If the charge, electric charge, is zero, then for neutrinos a question appears whether neutrino is Majorana or Dirac particle. It is very fundamental. It's one of 2, 3, 4 most fundamental open issues in neutrino physics. Like, what is the mass of neutrino? What is the nature of mixing? Why this mixing have originated in the theory and confirmed in experiment? So, and another question is, what is the nature, as people say? Because once you solve this question, and there are many experiments that aim to understand, to see, because in experimental it is possible to see. There are some new processes like neutrinos with double beta decay, probably have heard about this, that can proceed only in the case of Majorana neutrinos. In the case of Dirac, there is no. Also, there is difference, big difference between possible values for magnetic moment, the absolute values for in the case of Dirac or Majorana case. Yeah. Also, the Majorana neutrinos in the theories, realistic theories, can have much bigger magnetic moment than in the case of Dirac neutrinos. Well, and what is concerned again the particular properties and particular values of magnetic moments. Of course, obviously, the diagonal magnetic moments for the case of Majorana neutrino are forbidden, because there is a CPT invariance theorem. If particle, yeah, 2 minutes. So if you just believe in CPT invariance and it rule out the diagonal magnetic moment of neutrinos, but if in this interaction neutrinos change its type from mass 1 to mass 2, then CPT constraints are not applicable. So it means that in the case of Majorana neutrinos, neutrino can have magnetic moments, but transition magnetic moments, of diagonal magnetic moments. This is also very peculiar property of Majorana neutrinos.